Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud, and today we're going to start our new series on Borefield physics. Now, with GHEtool Cloud we made it easy for you to calculate even the more complicated and hybrid projects, but it's also our mission to educate you on what's behind the interface, on how a Borefield really behaves thermally. So that's why we decided to create a series of articles and over on YouTube related to the physics of the Borefield. Now, it's not our goal to make this on an academic level. There are other sources for that, and perhaps we will dive into that more in the future. But we really want to show you how you can reason about your Borefield with as little maths as possible. And today we're going to start this series with thinking or reasoning about something that's called the Borefield quadrants. But before we can get started, we just need to talk a little bit about terminology. So when we talk about Borefield physics, it's important to make a distinction between the building site loads and the ground or geothermal loads. So the building site is also called the secondary load, and the ground or geothermal site is called the primary load. So typically when we talk about building loads, we talk about cooling and heating our building, or even sanitary hot water, but that's another story. And when we talk about the geothermal loads, the primary loads, we are talking about the injection of heat and the extraction of heat. So the terminology is a little bit different, but they're related, of course, because when we say, well, our building requires cooling, or we have a cooling demand, this translates to the geothermal terminology of we are going to inject heat into the ground. And when we are heating our building, we are extracting heat from the ground. And it's an important distinction between because the building load is not the same as the geothermal load because there is a heat pump in between. So your building load in heating will always be higher than your geothermal loads because the heat pump with its own electricity consumption will take part of the heating load for itself. So in order to make sure that you do not oversize your Borefield, it's important that we know that there is a distinction between heating and cooling and injection and extraction. So in this series we will be mostly talking about injection and extraction to make the distinction as clear as possible, but just be aware of the difference. Another important aspect is called the balance or the imbalance of the ground. So if we have more heat injection in a year than we have extraction, then we heat up the ground year after year. And if it's the other way around, then if we have more extraction and injection of heat, then the ground is cooled down year after year. And this yearly difference, or this evolution of the ground temperature in the long term, is called the imbalance. So the imbalance is defined as the yearly heating up or cooling down of the ground. And a term that's somewhat related to the imbalance is called regeneration. And that's where we actively work against the imbalance. So we're actively addressing the imbalance or the heating up or cooling down of the ground. So if, for example, we have the situation below where we have more extraction than injection, we know that our Borefield, due to the fact that we extract more heat than we inject, will cool down year after year. And we can compensate for that by placing, for example, some solar collectors, some dry coolers, or with injecting waste heat in the ground or aquathermal energy. It does not really matter, but as long as we regenerate the ground, so we provide our system with some extra heat injection, then we can compensate this imbalance by using regeneration. Now, regeneration is a whole other story. It's not that easy always to implement, and we will make a video on how you can use GHEtool for that somewhere in the future. So now, with this terminology set in place, let's look at some temperature profiles. In case you have not seen our video yet on how to interpret temperature profiles, please go ahead, it's linked down in the description below. But this is typically a result you get out of GHEtool Cloud whenever you do a simulation, this case with a monthly resolution. And what you can see here is that we reach our maximum fluid temperature limit of 16 degrees in the first year of our simulation period, but we have a negative imbalance. The ground cools down year after year. Now this building, for example, is an auditorium in the climate zone of Belgium, where we have typically a higher heating demand on a yearly basis, but we have high cooling peaks because it's an all-air system, for example, and that's why we need to design our Borefield to be able to cope with this cooling peak in the first year of operation. Now, of course, we can also have this situation where we have, again, a limitation by the maximum average fluid temperature, but now our Borefield heats up year after year. So in our climate zone, that can, for example, be an office building, which typically has a lot of internal gains. But if we place also a data center in this office building, we can more or less be sure that we have more cooling than heating demand. So here the imbalance is the other way around, heating up the ground year after year. We can also see a figure like this, where we again have a negative imbalance and we now are limited by the minimum average fluid temperature. This is typically the profile of a residential building where there is a lot of heating demand and especially sanitary hot water or domestic hot water demand. So we're limited by the minimum average fluid temperature. And perhaps you can already see me coming. We can also create a figure like this. Now this is more of a fictitious image. I have not seen a building like this in real life, but it's theoretically possible. Now if you have a project that looks like this, please feel free to share it. I will be really interested in learning how or what type of building behaves like this. So we now have seen four different temperature plots, and we can arrange them into quadrants. So this is the concept of the Borefield quadrants. Every Borefield you will ever come across in your life, in your career, does not really matter, can be divided or classified in one of those four categories. Because every Borefield is designed to be either limited by the maximum average fluid temperature or by the minimum temperature, and it's either limited in the first or in the last year of operation. And okay, well, why does it matter that we can classify Borefields into different categories? Well, it can be used to make assumptions or to gain knowledge or insights from your system without even starting reasoning or doing different complicated calculations. Because if we, for example, have a discussion talking about the imbalance and we're talking about the investment cost of the Borefield, and someone says, well, if we place regeneration to reduce the imbalance, will that reduce the investment cost? You can answer this question without even calculating anything. Because looking at this figure, we know, okay, the imbalance is an effect on the long term. It's the yearly heating up or cooling down of our ground. And all those four figures have an imbalance, but only in the figures on the right, this makes a difference. Because here we are actually limited in the last year of operation. So if we decrease the imbalance there and we straighten the temperature profile, let's say, we can decrease our Borefield a little bit because we are no longer limited in that last year of operation. When you're limited in the first year of operation, the imbalance does not really matter because it does not impact your Borefield size because it's determined by the most critical point in the first year of operation. Another question is, when is drilling deeper or making your Borefield deeper advantageous? Now in Belgium we have a regulation where if we do not drill below a certain depth, typically 150 meters, then we do not have to file for a permit. So people mostly stick to that threshold there. But from a thermodynamic or HVAC point of view, sometimes it's better to drill a little bit deeper. When we're limited in the last year of operation, or let's say by the minimum average temperature, it can be beneficial if we drill deeper because then the average ground temperature is a little bit higher. So all the lines move up a little bit and we can again decrease our Borefield size or the number of boreholes a little bit. Now if we're limited by the maximum temperature, drilling deeper is disadvantageous because then again our ground will be a little bit warmer and this will make the problem with our heat injection even more pronounced. So only in quadrants 3 and 4 is it beneficial to use a deeper Borefield. The other way around is when is active cooling advantageous? Now active cooling is mostly advantageous whenever we have a problem or design that's specifically done for cooling. So whenever we're limited by the maximum temperature, it can be interesting to shift to active cooling just to lessen the design criteria there. So we can move from, for example, 16 or 17 degrees for passive cooling to 25 degrees for active cooling. So we can decrease the number of Borefields because we're no longer limited by that strict maximum fluid temperature. So this was all I wanted to say in this short first video where we talked about the Borefield quadrants. In the next video we will be diving more into the physics, talking about what's behind those temperature profiles and how your inputs from GHEtool relate to these outputs. And we'll be talking about short-term effects, we'll be talking about power, about energy, we will be talking a lot about imbalance, thermal interference. We will cover it all for you. So in case you think this is interesting, please consider subscribing or sharing the videos. It will really help the community, and I hope to see you in the next video. Take care. Bye.